So, a quick response to this solution posted for number 8. It's pretty close. I just wanted to make a few comments about it. Number 8 has to do with when A is equal to A star, the eigenspaces should be orthogonal. Now, what we assumed is that we've got A times V equals lambda V is one kind of eigenvalue eigenvector pair, and the other one's AW equals mu W is another eigenvalue eigenvector pair. And this is the basic argument that's correct. Okay, what you guys did was said that lambda times the inner product of VW. Then they brought the lambda in because of linearity. Then it becomes a times v. That's great. Now they moved the a over to the right part of the argument for the inner product using a star. And this is where it just gets, there's a little issue with a star w equals mu bar w. So let me explain. Because A is self-adjoint, A equals A star, you can actually say that the eigenvalues themselves are real. Okay, so at this stage what you could have said was this inner product V A star W equals V A W equals V mu W, and then you can just pull the mu out for free, okay? Instead of it pulling out as a complex conjugate, because the mu is real. So here, let me try to explain. In general, if you just have a square matrix and an eigenvalue eigenvector pair, it is true that so this is V lambda is my eigenvalue eigenvector pair. It is true that lambda bar is an eigenvalue of A star, okay, just by looking at this little determinant equation. But you don't always have the same eigenvector for A star. Okay, so here's a quick example. When in the non-self-adjoint case, here's my matrix A. Lambda equals 0 is an eigenvalue, and an eigenvector is 1, 0. But when I take A star, it's same as A transpose. It looks like this. You still get the same eigenvalue of 0, but the eigenvector is different. Okay, and so this replacement in general, where you go from A star W to mu bar W, is generally not true. It is true this time because A equals A star and mu equals mu bar. Okay, so yeah, basically that's where the little logic problem is. It's pretty damn close to being the correct answer, but I wanted to just point out that there's something that's a little bit fishy going from here to here, and I can see you kind of forced it so that you could pull mu bar out and get mu here. The rest of the argument's cool, it's all fine. Like I said, the one thing that is kind of missing is all self-adjoint matrices have real eigenvalues, and so here's a little argument for that. Suppose that A equals A star, and you've got this eigenvalue eigenvector pair, V and lambda, and then just do the quick inner product. AV inner product V, replacing AV with lambda V. Pulling the lambda out, you got lambda times V inner product V, or lambda V squared. The same thing, starting from the same point, AV inner product, that's supposed to be a V, is V inner product A star V, which is V inner product AV, because A is self-adjoint. So that's V lambda V. So lambda bar comes out, and it's lambda bar V squared. So what we've got is lambda V squared equals lambda bar V squared, so lambda equals lambda bar. So, so the eigenvalue is real. And so you can actually just use that here. You can use this idea that mu bar equals mu, and we don't really have to worry about that that little logic problem that I wanted to talk about.